Hello again, everybody. Kind of rushed yesterday. I'm glad we got off to a good start today. Hope everybody's doing well. I'm on a residential bandwidth, so I'm going to kill my video. I will be watching the chat room. You're welcome to pipe up at any time with any questions you've got, of course, on the audio link as well. With the residential bandwidth, sometimes my video ends up slowing down everything. So welcome back. Let's talk a little bit today. We made a special presentation for this class and for you guys. Understood a little bit more about the background you've got. So we put this together before the last time we did this. And today we're going to cover regulators, including governors, and electrical protection for distributed generation systems. It's going to move along pretty quick, but feel free to come up at any time and love to have your feedback and questions. So a quick first one will be kind of a fun look back. This is, if we advance, 1860s steam. Actually, see the thing work. You want to draw your attention to the one thing.
I would tell her to lower the volume. We can't hear you.
Okay. That was trying to show that the noise, the background audio was too high. Okay.
The video was coming in too loud.
Oh, okay. Sorry. See if I can turn that down a little bit. I'm just gonna play now. Well, no, it doesn't want to play at all. Okay. Anyway, I want to draw your attention here to the up on top. There's a fly ball governor up there, and it spins. As it spins, the balls raise up and go out due to centrifugal force, and that opens a valve and that closes a valve and causes it to. So back device that they devised, and this is 1860s technology on this unit. Not sure why I can't get it to play again, but maybe we can here. Is that a better audio level? Yeah, see the fly ball. That's really what I want to draw your attention to. It's old antique piece of equipment. Got the pump, it's got the regulator, the flywheel. It's still out there. With the fly ball gun. So let's talk a little bit about how the fly ball gun and how governors in general work, and the regulator function. So regulators are used to control a particular condition. Now, series of regulators can control several things at once, but generally a regulator controls a thing. And there's some kind of variable in the operating system. And this is the theory, and the mathematics behind it were all developed by old Elmer Sperry back when ships in the early 1900s. But it's interesting that they established a reference. That is going to be the middle of the channel, and the feedback is the actual position in the channel. And he says there's a difference between these two that is added together into a summing junction. And then a mathematical formula is applied to this. And this, you do this all in your head automatically when you drive, when you do things. But he put the math behind it. And the formula was kind of complicated. And there's a lot of discussion of how to properly tune the system. But if we break it down into something pretty simple, maybe it's a quick and easy way to understand what the regulator is trying to accomplish. A simple example that you use when you drive would be your cruise control. In this case, we've got a little engine and a little car, and we have a 4-cylinder engine, so we have a gain of 4. We have a reference in our. Let's just say that it takes 20% throttle to maintain 55 miles an hour on flat level ground. And that's not an reasonable figure. Obviously, you shouldn't be using full throttle to maintain 60 miles an hour on flat ground. If so, you got something wrong with your car, overloaded or something. But 20% is a reasonable value of torque needed to push that car down the road at 55 miles an hour. Well, if you set it for 60, and with a gain of 4 here, to get 20%, you need 5. So the speed will actually be dropped down to 55 miles an hour, giving you a difference of 5 times 4 will give you 20. If you older cars, or those might remember the earlier cruise controls, you actually felt this. You'd punch the cruise control and the speed would drop a little bit, and you'd pick up and run at that new speed. And so you'd bump the speed increase a little bit to get to your 60 miles an hour. So this is an okay regulator. I mean, you might say this is not bad. You don't really get 60 when you set it. And how could we solve this problem? Well, let's just turn it up a little bit. Let's get a little bit bigger engine, which means a little bit more gain. And so now we set at 60, and with a gain of 50 to get that 20% still, that didn't that level ground. To get our 20%, now we only have to go 59.6 miles an hour, or excuse me, only have a gain of 0.4 difference times 50, which means a 59.6 miles an hour. That seems better. That seems good, doesn't it? It's like, wow, we actually can get a better speed out of the unit, closer to what we really wanted in the first place by doing this. But what would happen if you took this uphill a little bit? Any feedback I'm watching or listening? If you started to go uphill and your speed dropped off 1 mile an hour, you'd get full throttle, wouldn't you? Right? Because a 1 mile an hour difference would be 1 times 50, you go to 50% anyway. So if 2 miles an hour would give you would floor it at 100% power. So it actually starts to get unstable. You could actually get to the point where it becomes a natural resonant frequency, and that's where you speed up, you slow down, you speed up, you slow down. Full throttle, that's too much. Back it off. You might have seen this in your power regulators, your watts and your bars swinging back and forth when you try to fight or try to push too hard and get too much gain. Well, natural resonant frequency can also be a problem, right? Here's a good example. All natural frequency.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now.
There's a car out there, a dog in the car.
There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick.
That's a lot of force because the wind was blowing and it caused the bricks to go. And that's the kind of power you get from natural resonant frequency. There's so long
Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saves himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes!
So natural resonant frequency is not something you want to have to happen very long. And this overshoot we have to control so it doesn't get into this resonant situation. And again, if we could increase more gain so that we could go closer to 60 when we set 60, but when we got into a transient condition, we can reduce the gain, right? So turning up the regulator in a steady state condition doesn't really tell you much. And we actually used to hand out screwdrivers to people who were doing regulator tune-ups on drive systems. And here, tune them up, turn them up. The young engineers would go out and spin them up. Oh, the gain's going better. Look, it's going better. They would call it job security, because sure enough, we'd come back later on and have to retune it, because they would tune it up too high, and it would get to the point that would make it unstable during the transient condition. So transient conditions are when you really should be tuning, measuring, not steady state conditions. So if you turn the gain up during steady state conditions, yet turn it down in transient conditions, how can we do that? Well, we do that in the integrator. This is what the I does in the PID. The integrator actually slows down the regulator, but the advantage is a steady state error approaches zero. So we get more gain during the initial part, but as we move into other parts, the gain reduces over time. So that's what the integral function does. So that's the proportional is like the 4 or the 50. That's the gain. The integral actually slows it down a little bit during transient conditions. But wouldn't it be good if we could look ahead and see what's coming? You do when you drive, right? You see a hill coming, you might step on the gas a little bit. It's something called feed forward. Well, we really can't do that in our closed loop systems. We can respond as quickly as possible. We really can't feed forward. There are technologies that are looking at doing that in naturally resonant systems, for example, MRIs. That thump, 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 thump of an MRI just plays on generators. And so they've been able to do things in the system because we know that's going to continue for a period of time. So with that thump, 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 thump that happens, we can sometimes bump the gain. We can increase the reference a little bit, knowing that we're going to have more problems in the near future as this MRI continues. So feed forward isn't really used very often. It's very specialized technique, but really can't do it in everyday systems. So now we offset the slowdown. So we added the proportional. We increased the integral to slow it down. But we want this transient condition, during a quick transient condition, we want to add some gain. We want to add some gain during the rate of change of a signal. So if we drop off quickly, we want to hit it quickly. So if we add a impact load, let's say we drop a large load onto a generator, a large motor load, for example, we want to boost, we want to kick that AVR, we want to kick that governor in hard and fast. And that's the differentiator. So the D in the PID is rate of change. Okay, so think that proportional is gain, is response. Integral slows it down, and differentiator comes in during is rate of change. So it adds some gain during rate of change. So quick look, and this is a step response. We applied let's say stepped up the increase to a unit, and was a slight deadband up front, but then we jump up and we respond to this input disturbance to the system. We add more fuel, we add more excitation boost if we need to. But we have to ask ourselves, can we live with this time delay? What if we had this MRI load that goes bang, 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 bang? Well, a lot of generators, when they first brought those on, would step down and recover. So you're at 60, you jump back to 59.6, and then you jump back to 59.2, and then you jump back to 59, and then next is 58.7, and you just find yourself dropping off because you never really fully recovered from those impacts. So in that case, you could not live with that time delay. You'd have to do something to make it respond quicker than that. Otherwise, you'll just hammer it into the ground. So a large load step input. And then also, can you live with a steady state error? Now, for a long time, the system today still exists on about a 4% group. That is, as you draw more power during the day, the frequency comes down, and it's the utility's job to average the frequency out over 24 hours to keep clocks on sync. That was their job for a long time. Well, now clocks are digital, not such a big deal. Computers are much more forgiving of frequencies than they used to be. So this strive to maintain very, very, very accurate frequency and voltage. This pressure's kind of come off on that a little bit. We're not as worried about frequency and voltage today as we were, and that's a good thing, because the smart grid with IFG wouldn't be nearly as successful if we had to maintain a very, very tight frequency band like we used to 20 years ago. So can you live with this steady state error or not? This is a question you have to ask yourself when you're looking at analyzing the system. So here's P controls critically underdamped. That is, we have put too much on it on purpose because we want this fast response back to this point. We're going to overshoot a little bit, but in a voltage regulator, that's really not as much of a problem. But when you're talking a fuel regulator, the fuel system and mechanical of a generator, that may not be so good, right? I mean, mechanical flexing of the coupling, bang, 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 back and forth, can cause problems. So this 3-bump tuning, we used to call it, actually is a term for it. We used to set up excitation regulators at small steam turbines. By doing this, we turn them up and watch the needles swing 3 times, and we disturbed it. So it was okay to do that with voltage, but not with throttle or fuel. So here's PI controls, and for a long time we lived with PI. PI was it for generations. PI is all we had. We didn't have D. So PI properly tuned. You got some options. We have a little bit of overshoot. Our steady state is okay. Our response time is quicker. So PIs properly tuned are okay. We have to ask ourselves, the nominal steady state error is less. The response time, that may still be a little bit too long. We may not be able to respond quick enough, or we might hammer ourselves into the ground, which what we saw with the MRI, and that's why they started developing the D, right? If you increase your P gain too much, you run the risk of overshoot, and that's not a good thing with a mechanical system. You get into the concern about natural resonant frequency. So with PD controls, this is no I, just PD, we actually can increase during the acceleration portion. We add more gain to it, but we kind of get into this overshoot situation a little bit. This PD controls have a real high risk of overshoot. And again, that may or may not be a problem, but generally in mechanical systems, an overshoot can lead to eventual long-term mechanical failure of some kind. We do our steady state error is reasonable. It's not too bad, but our response time is quick. We brought it up quickly, and we fixed that hammer into the ground problem with the MRIs. So here's a PID. So once we went to the MRIs, we started to add D. In this case, we have PID. Our step response is still there in the green. The blue is our actual values of speed or voltage as we responded to this disturbance. And you see it's properly tuned, good interval gain, good differential gain, and with almost identical response to the system. And that's a very good, very well-tuned regulator, kind of optimum, if you will. In diesel engines, we don't use D a lot unless you get into something specialized. Perhaps marine environments where the load is close to the generator rating. So typically you'll size a generator, 1.5 to 2 to 1 to the largest motor. You might end up being closer than that. You might need some D to compensate for that. P and I are good enough. In most cases, a PI regulator is good enough, but sometimes you might need D. We were doing marine applications, and we had one of the marine tests, I think for the outfit in England, I forgot the name of it, but they're a certification agency. And you actually had to drop a 70% load on a generator from 20% load to 90% load. And you had to recover in a certain period of time. And D really helped us to meet those needs in that case, adding some D into the system. So it might be used where it has to accept a large block load, for example, but it's not often used very much. But a little bit of D sometimes can help your system. So that's kind of a quick theory behind PID. Looking for any questions in the chat box, or anyone holler up if you have any questions. Before we go on to the next one, we're going to talk about what regulators are used in gensets. So Not hearing or seeing any questions, we'll move on. We'll ask ourselves, how many regulators do you think are used in today's advanced genset controller? Anybody have any idea how many regulators we're tuning up here? Watching the chat box.
Can you repeat the question, Steve?
How many regulators are in today's genset controllers, you think? Is my audio good?
Yes, you sound good.
Okay. No guesses out there?
3 regulator?
Yeah. How many regulators?
He said 3.
3.
3. That's a good start. That's a good start. That's a first good guess for a lot of people, but actually there's more than you might think. Speed, obviously, for a single generator feeding a single load, you regulate speed, which of course is frequency. If you also, with that single generator feeding a single load, you'll have a voltage regulator regulating the voltage. But when you parallel those machines with another one, you have to look at kilowatt. So now if you say you put one generator against the grid, once you close your grid breaker, you normally go to a kilowatt regulated system, kilowatt and kilovar. So kW and kvar regulated once you tie with utility. But if you tie several gens together in a PPI, a parallel power island, now you have to load share. So you'll have a load share regulator to balance the loads between the generators and regulate that so you don't get into a resonant situation where, you know, one kW swings up high, one goes low, and back and forth and back and forth. Synchronizing regulators are also needed. As you synchronize a gen to a gen or a gen to utility, you have to bring your speed up close. Then once you get your speed within a few percent, maybe half a cycle or so, then you'll turn on a phase angle regulator. You'll actually look at the phase angle difference between the generator and the source you're syncing to. You'll actually look at that phase angle. So several of them actually could be in today's genset controllers, and they all have PID values that have to be tuned. So don't underestimate the value to your system of a good tune-up, and don't overlook any of these regulators when you're doing your tune-up, because maybe you're only running a gen and load combination today, but tomorrow you may run multiple gens in parallel with each other and may have to come back and retune them, because if you have 2 or 3 generators feeding the same load, their response times need to be very close. Another example is they have to be active at one time. So if you have a parallel power island, you could have speed and kW and or kW share, volts and AVR all can be active at the same time. So many of these are active at the same time, and as you know through your power triangle, volts, amps, and watts react with each other, right, as you see in the power triangle. So they can interact with each other with the regulator. So if you increase your volts, you might actually increase some watts some. Even though you didn't adjust your watts any, it still might result in an increased watt flow. And then having 2 generators feeding a single load, when you get into this regulator interaction. And this is really important in parallel generation, so you don't fight each other. I like to use the example when I'm driving down the road and the wife's next to me. I'm driving, and she's going, "You're going too fast. You're going too fast." Well, there's 2 of us regulating quantity. I got the control, but she can be in my ear telling me to slow down, and that is 2 regulators interacting with each other, and this interaction can cause resonance as well. So be careful of regulator interaction between regulators in the same system or regulators in parallel gensets, for example. Okay, that's a quick background on regulator and regulator theory. Let's talk a little bit about governors. Still watching for any questions. If you have any, feel free to drop them in the chat box there or speak up. So governors in today's systems, the fly ball governor, I showed that video of early on. The spinning fly ball governor developed a long time ago. The faster you go, the balls push out centrifugal force, and that's where the term balls to the wall came from, was that all the way out as fast as possible. And then the electronic governors by various different makes and brands, they've gone from purely mechanical to mechanical hydraulic to pure electrical nowadays. So they've evolved quite a bit over the years, and obviously you get a lot of flexibility with your control systems as well. But a governor really is set out to maintain or limit a function. In this case, most often it's speed and the governor. The voltage regulator does the volts, governor does the speed. And the question for you is what actually, and again, I don't read every word. Feel free to read this as I go along. What does the governor in these systems actually affect in the system? What's the output of the governor actually does what? Increases what? Anyone? If the AVR controls the excitation, the governor controls what actual physical quantity?
If you are able to unmute, you can answer.
Okay, well, it's fuel. I guess everyone's busy today. You actually increase the fuel. If you increase the fuel or decrease the fuel, as you adjust the fuel, you're adjusting the torque, not the speed necessarily, because the total torque produced out of an engine is a sum of the load torque plus the torque of accel or decel, sign dependent, plus the losses. Losses go up with speed, but the total torque actually goes into load torque. And I say it that way carefully because if it's a single gen, single load, increase fuel, you'll increase speed. Single gen, parallel with utility, increase fuel, increase torque, which increases the kW output. So governor, although it's affected by kW, it's actually controlling the fuel, which is actually torque, not speed, not watts necessarily, it's torque. So the governor controls the speed during single generator, single load configurations. Centrifugal force is sometimes used in the old mechanical governors, and today it's a digital system. And of course, you're trying to maintain 60 hertz. Governor also regulates real power when it's parallel with utility. Single gen or parallel gens on an island system, so the governor controls the speed and the frequency only. Synchronizing, when it comes to times to synchronize, now you're adjusting the fuel a little bit in order to pull these generator into synchronization with either a utility or another generator. So during synchronizing, the frequencies need to be matched, and then the phase angle needs to be matched, and then we leave it up to the AVR, of course, to match the voltages and get them pulled as close as possible. So it can be done by some external device or part of the governor. When you're looking at let's say a generator with a local load and a utility tie point, and now you've isolated from utility, run an island mode for a while, feeding your loads, and now you want to go back on utility, you synchronize back to the utility, and now the genset controller may not be able to see that tie point. You may have another control device at that utility tie point sending a speed trim signal back to the governor on the generator to get it to match utility. So the point of synchronization, you've got to have obviously BTs on or voltage detect on both sides of the generator breaker. So synchronizing is another governor function. as well as the air-fuel ratio mixture for gaseous engines. You want to control and reduce your hydrocarbons. So it's this isometric, stoichiometric and isometric, sorry, points on the curve where you want to maintain emissions. So the governor controls the emissions, if you will, or the fuel ratio in order to get the right emissions. It does timing. So if you're on a spark engine or controls the spark, or if it's a injector, it controls when the injectors inject fuel into the cylinders, but it's all done by the governor function, right? It also, the governor, hello, how did it go? Oh, there's a little, there we go, sorry. And then there's a knock detection and control that takes place that actually will detect knock or post or premature ignition of the gases in there, whatever the heat sources being inside, and it'll try to detect those and prevent those. Obviously, if you have knock, you could end up with destroying an engine in some cases. So governor does a protective function in this case when it detects knock and eliminates that. So this is just some of the pieces that the governor controls. And of course, it does this by this closed loop process we talked about before, the PID regulator. I'll show you one here, and this is just one. There's a bunch of them, but this is probably the most complicated, and we'll sum up the regulators. But if we're driving the generator over here on the right side with the prime mover, we're checking frequency here, and we have a speed control with the desired speed reference, 60 hertz generally in our industry, a PID regulator, which drives an actuator, which drives that prime mover. So here your primary initial loop is speed. Right? As you start to bring in more power, say that you're going to synchronize across the breaker here, you have the two signals coming in, the gen phase and bus phase, and they're summed together. They drive another PID for your synchronizing that provides a speed trim signal to the speed regulator in order to bring it into synchronization. And once you're synchronized, then that one's turned off. That was turned off. The speed is kept there, but that's turned off. And once that's closed, now you're providing a watts into your system. And so now you have watt feedback with your KW sensor looking at your voltages and your currents, producing a KW signal and a kVAR signal. The KW signal goes into your load reference. So now your load regulator, that is your KW regulator, PID for the KW regulator, provides a speed trim signal into this regulator. So because we have multiple regulators running, the time constants have to be set so they don't interact with each other. Typically, you'll set the in loop faster than the outer loop so that you don't have this oscillatory effect. That figure normally is 3-to-1 response away from each other if you're measuring response in radians. It also has this KW, kVAR sensor also feeds back bars, since here's your VAR regulator and the PID in the excitation system. So this is all going on at the same time. Has to be tuned properly. That kind of summarizes, again, we talked the regulators in a system here. And as a reminder, we covered this before, but the torque as a fuel is a governor. Sometimes it's in the ECU, sometimes it's in external controls, but there always has to be something in control of the fuel, and they have to work with each other. So sometimes there'll be an external governor and an internal governor, and they have to work together so they don't have interaction between the two of them. Of course, voltages later is another consideration. I'm not downplaying voltage. It's just usually easier on voltage because the response times are faster. It's the mechanical systems and the possibility of natural resonant frequency that drives us to be very careful how we set the governor. So that kind of runs the summary of the theory of PIDs and the regulators used in today's gen sets, what they're used for. Let's move on to the next thing. Again, don't see any questions. If you do, please speak up. Next, we'll talk a little bit about galvanic isolation, and this is a little bit tongue-in-cheek, but it's actually happened. So history sometimes is funnier than reality. But back in 1791, this old guy Galviani here, he was playing with he'd taken frog skins. He's taking frog skins, blowing air into them. You guess whichever opening you want to use, rubbing it on wool, producing a static charge, and you see the frog muscles twitch. So truly, he really thought that electricity came from frogs. He was going to hard to make this stuff up. He actually wrote big paper and was adamant that there was going to be here, and he was going to make these mega factories, big frogs. They'd feed them ground up frogs to make bigger frogs to make electricity. Not making this up. You can't make this stuff up. In summary, I guess 1790 was not a good time to be a frog. Okay, he was actually going to make these frogs. Well, about the same time, his buddy Alexander Volta was playing with dissimilar metals, acids, cardboard, tin, this kind of thing, and he was making this carbon pile battery here. And this is a picture of his original battery that he made out of wood, bolted together, and he'd stack these materials in here, and then he'd put acid on top of it to create this battery effect. And he had no way to measure it. There was no voltmeter back then. And he touched the terminal and say, "Yep, that hurts. Well, that hurts a little bit worse." And so he was playing with electricity back in 1791. And these two guys wrote papers, fought each other, almost like our Republican and Democratic parties today do, right and left, right? Turns up that old Volta was right. Galviani was an unknown voltage source. They were kind of going back and forth at each other. And then you can see Galviani here's got his frog on his plate, and Volta's standing on top of this carbon pile battery. But technically, at the end, we all know Volta won, right? Because volts was there. But galvanic isolation means you want to isolate yourself from these unknown currents. This is energy that's some other source or unpredictable source of electricity. And where could that be? It could be static. It could be ground loops. It could be results of induced voltages into systems. But you want to isolate these systems from each other. So when you're in the process of creating, developing, specifying, starting up a control system, we have to be very careful about galvanic isolation, make light of it because it all came from a bunch of frogs. But it's really important to isolate these two circuits from each other. And where could these currents come from? Well, it could be induced currents, like parallel wires in a cable tray. It could be a fault-based DC offset in something, a temporary DC offset. Like we had this control company I was working at back in Illinois. We connected the PC to the controller on the Modbus port. And at the time, our PCs were only, on a cart, plug-in AC powered. They weren't laptops back then. And so when we plugged the Modbus port in, we grounded the switchgear through the Modbus port and blew the Modbus port out on the controller. So it does happen. And also when you have a fault condition, as we know, the faults are common. Usually 85% of them are line to ground faults. 24% start in the switchgear and 7% of the generators. The rest of them out of the distribution system somewhere. And there's asymmetrical. So when you get a fault, it jumps up to a high value and then decays with this DC component in here, L over R ratios or other. And this DC decay component is what actually can cause a source of induced or galvanic currents as well. It's important to have this galvanic isolation to prevent these from causing a problem. A quick example of how a fault can do it. Let's say you a fault in the switchgear, and Gen 1 is the closest, Gen 2 is further away, and Gen 3 is even farther away than that. You have utility source in here in play as well. Of course, utility impedances are generally lower, so you get more fault current from a utility. Gen 1 is the closest, and so his impedance of his cable is the least. And so you have a fault in here from A to ground, and through this fault comes back to the switchgear ground, switchgear frame to the bus, and then back to the neutral path. Of course, Kirchhoff says anything that goes out, it's got to come back. goes out to scatters equals goes into, and the current's got to flow back to the source. So let's look at this in just one leg of one generator parallel setup, and we'll look at the A phase. So if we have one generator winding that's generated 277 volts, let's say, and there's a common ground point, the ground got cut off there at the bottom, I apologize. But out of this generator winding, there's cable and the circuit breaker and bus impedances. So the cable from the generator to the switchgear bus to the breaker contacts onto the switchgear bus itself, and then the bus is where the fault was in this scenario. There's a fault impedance. That's the arcing, burning impedance of a fault. It varies with intensity, of course, with the impedance of the fault, but is definitely impedance there. Then it jumps to the switchgear frame and goes down through the sheet metal of the frame. And often the drain wires from PLC's controllers are connected to the switchgear metal frame. And so they might be connected there. There's an impedance in the metal as the current flows down to the ground impedance, to the genset ground bus, to the to the neutral to ground bond connection, back to the Y and back to the center of the generator. So these are all the impedances in this circuit. And when we have this high current, this high fault current flow, we'll make up some voltages and put them in here. One was closer than 3. They're both doing 277 volts. So because one is closer, we're going to say that there's more current flow. So here it's 260 instead of 270 volts because we're dropping more current through here. The voltage difference here, again, due to the different amount of current flowing in Gen 1's phase A path versus Gen 3's phase A path, and causes a differential. And this is exactly what happened to us there was we had the PLCs and the controllers are here, and they're connected together with this little twisted shielded pair with a ground wire. So the ground potential between Gen 1 and Gen 3 is off by 4 volts, and that little wire is carrying lots of current in that 4 volts. And that was burning the controllers up on us. So these are circulating currents or galvanic currents, unknown. We now know what they are, but at the time we don't know what they're going to be exactly. So this is the isolation that we need to have place. And this is why galvanic isolation is so important. Some of the controllers are offer to take a less expensive approach, and they will insist upon having extremely good grounding systems such that they're exactly equal. And so the 3 volts in generator 1 is 3 volts in generator 3 all the time. And that's not really typical if you're in the real world environment. If it's in a powerhouse where they're next to each other, you can run a big ground bus across the ground, that's probably okay. But if you're a temporary installation with trailers and cables on the ground, that's going to be really hard to get a good solid ground connection. And so you want to be careful of that when you're doing that. So we need to specify galvanic isolation on our load share lines, our bar share lines, all these analog signals. Digital's not as much of a problem anymore. The new digital controllers, whether using CAN bus or others, it's not a problem. It's a differential signal. You don't connect the grounds. You don't worry about it. But in analog systems, you definitely have to be very conscious that that's a galvanically isolated signal. To get this galvanic isolation, you can do it digitally with relays. That's most obvious. You energize a coil, the contact closes, those circuits are totally isolated from each other. It's a way to share information from this circuit to that circuit. Maybe it's a 24-volt coil and a 120 volt. So different systems, different voltage levels, but still it's a way to provide this galvanic isolation between the systems. Magnetic flux isolation is another one. This is used, obviously quite a bit in AC power circuits, CTs, PTs, things like that. Excuse me. They also have small transformers on circuit boards that are used for isolating signals. Your CTs often come in to a controller, and before they get A to D, analog to digital converted, they're dropped down to a low level through little onboard transformers, drop down to some low level. So magnetic flux is another force. Another type of galvanic isolation is optical isolation. And these are optical phototransistors. It's the analog signal. Sometimes it's chopped and then filtered at a high frequency. But at any rate, it's optically isolated from this light emitting LED to this receptor transistor here. It's good isolation. It tends to be a little more expensive though, because you have to have an isolated power supply for this circuit and a different power supply for this circuit, because the power supplies would then tie it together, wouldn't they? So you have to have an isolated power supply, which costs money. So we have to get this optical isolation involved in here, and this is the third type of galvanic isolation, and why it's so important to our control system to electrically isolate one system from another. Okay, so that kind of wraps up that point. We talked about regulators, talked about regulator theory, and some how they work. We talked about galvanic isolation. So now let's get a little bit more into the control system. Still watching for any questions, feedback. If I'm going too fast or too slow, let me know that too. I'd be glad to speed up or slow down as needed. We're about 1 hour, about halfway through. So how does galvanic isolation relate to the system? The control system should be galvanically to system ground, okay? The galvanic isolation, let's take, for example, the older analog load share lines were 3 volts, plus or minus 3 volts. You would use those lines to balance load between control systems. If the ground at one point was different than the ground at the other point, even if it was just only during transient conditions, that ground potential would be different, that 3 volts would be different. And so you might end up with forcing the generator on harder than the other one, because it would see that difference in that voltage. So there's control systems with galvanic isolation, and then the power system with this grounding system, 2 different types of considerations. But the galvanic isolation that I'm talking about now has to do with the control system. You do have isolated grounds, like hospital grounds, building grounds. You may have a generator feeding 2 different buildings, and they want to put a ground rod at each building. Well, that's not a real good plan, okay? Unless you have with one generator, because the generator wants to be grounded. So that's another form of isolation required. I'm talking more on the control system, galvanic isolation, little voltage signals and little control signals. So hope that helps. So let's talk. If you're welcome. Let's look at a new system. You're going to specify a new system for a power plant or for an installation of some kind, and you have to ask yourself, how much control do I need? Right? Control systems can be cheap. It's literally a key start, right? Push button start. They can be very, very expensive. So let's try to structure the controls that we need for our system. Understand a little bit more about what functions we might need, and what the cost might be for those functions, and how we pull them together. Control system complexity can be, varies a lot from a 15 kW residential unit to a 2 megawatt, parallel with utility, parallel with other gens system. The control system is varies widely. And in fact, you can have a very expensive control system with expensive components, even doing the same thing. So you can put a 2 gens on a parallel power island, and the whole control system can cost you less than $10,000. Or get 2 gens in a parallel power island with a custom controls that are going to be $50,000. A lot of it depends on what's the application. Is it a nuclear power plant backup power supply? Is it several parallel generators feeding like a business load where it's maybe critical to the business, but in the grand scheme of things, it's not really all that critical compared to a hospital or things like that. So what is the requirements for the installation? So we're going to look one real quick here. And obviously, this is a big old gas or Waukesha. See the coils and the steam lines and all that up here. So the level of control here, it was going to be different. And here's the generator. with its medium voltage, I can tell because there's no breaker here. It uses differential relaying to accomplish that. But the control panel on here is basically a monitoring panel. It's probably monitored somewhere else. So the controls on there would be maybe 5 or 10% of the cost of the machine, but still very, you want to protect it. It's a very expensive machine. You want to provide as much control and protection as possible to minimize outages, minimize faults, things like that. Compare that with the chicken farmer generator, a little 20 kW unit. Somebody said this was a gas or a diesel. I guess I don't know what it was. But anyhow, it's very simple controls on this. The vernacular is a Murphy box made by Murphy out of Oklahoma, but they made thousands of these things. You got a voltage, amps, and frequency meters. You got an hour meter, an oil pressure, and then either a key switch or I can't tell what that's, key switch or toggle switch. But anyway, very, very simple controls. Obviously, it's got the engine ECU will do the engine protection, and the generator output breaker will do electrical protection. That's really about it. Right? So the level of controls are much different here. And here's the next step on the other side. This is a big a nuclear plant, and I think this is Nuki. Yeah, I think it is. But it's a large. So here's your steam turbine back here, and here's your generator. This is the doors you walk in and look at the generator windings. The doors you walk in. Here's your exciter panel on the outside of it. There's a nameplate back here. We'll zoom in on that and take a look at that nameplate. And that's it's a gasser, right? So hydrogen water cooled. So hydrogen cooled generator, along with a water, hydrogen and water. So they have a water to air exchanger in there to keep it cool. 3-phase Y connected. kVA 35,000 armature amps at 22,000 volts. A lot of power, right? Here's the turbine, steam conditions, 900 PSIG, 14 stages, and we'll see our speed on here. But anyway, this is a big one, right? And
1.21 gigawatts.
1.21 gigawatts. Well, it's 1.28 gigawatts of power in this unit, and its control system is very expensive, right? So here's the electrical controls on the backside, protection and controls, electrical distribution system, and here's all the mechanical stuff and the boiler and turbine controls and all that are over here. So obviously the control system got to be much more than what we're used to normally deal with. That just gives you kind of the spectrum of controls that are available. You can get just a key switch, like the top right picture. It's simply a key switch, stop, start, run. And it's got a couple shutdowns. In that case, it's got a voltage and an oil, and looks like a temperature shutdown, and a couple more you can program with clicks on switches. Less than $100, something like that. Single function components like this, you might use this. We talked the other day about if your inverter power, your IFG starts to push too hard and penetration level, it gets to be too high. That is, your generator actually starts to go into below its normal or below a safe operating point due to wet stacking, due lightly loaded. At some point, you'll kick in a kilowatt signal and say, okay, shut off the IFG. Well, that you can do that with a simple one like here on the right side, this Basler single function device over here. Woodward here has a load share module. It's got several functions built into it to do load and VAR share and the regulators associated with it. Here's a DIFE controller that's a dedicated purpose controller that'll do a gen and 2 breakers. There's open and close for the gen main breaker to the load bus, and a open and close for the utility breakers if you do it all in the same controller. Here's a Basler unit. I think it's pretty much the same as this unit. I can't see, the screen is not set up the same way right now, but it's very similar functionality in the DGC 2020. And here's a PLC. Now you're going to hear that I'm not in favor of PLCs in power generation control, and let me get into that in a second. But they're out there. They've been used for a long time, and you be aware that they have their place. Don't get me wrong, but generally, I think they're over application of technology because of the programming. Let's take one step back and look historically where the controls used to be, and this helps us to understand where we're at today. Level 1 controls are on the engine. Today they're the ECU, the ADM, the ADEC, whatever you want to call it, but it does the basic engine functions. It starts, cranks, emission control, fuel control. Used to be all individual discrete components. We used to make control panels up to do all this, but anymore it's all done by the ECU. Crank timer, over crank, rest timers, all that kind of stuff are all done in the ECU. So that's the engine protection, engine control. We had that the genset level. I put a generator on, I have a genset package. So this is the primary generator protection, over current, over volts, reverse power on the generator, things like that take place at this genset level. Backup engine protection. So the engine protects itself against over, at some temperature, it will trip. So, and your genset control, you can often prevent a trip by saying, I'm getting hot now. I see that my outlet temperature is getting too high. I'm going to unload this machine by starting another one and take some of the load off this one so I can do shutdown prevention, prevent a shutdown, right? Generator breaker control, synchronizing load var share, gen node selection is done at the second level. Again, used to be discrete components. Now dedicated purpose controllers are often used for this. And the level 3 was at the grid utility tie point. So this was synchronizing with utility, import-export mode, peak shave, peak lopping, IRC control, power management things that go on with multiple gensets. It has to have some kind of a master controller, and that's the level 3 control. So that was historically the 3 levels we had: on engine, on the genset, at the tie point. Today's electronic engines can actually put a lot of this stuff together into one ECU. I know that Cat's got some, Cummins has some, that they put all these level 1, 2, and 3 controls all in the ECU. It works. There's pros and cons to using proprietary controls versus unlocked and open platform controls. It depends on who's servicing them and how, quite often. Availability of service people. If it's a proprietary control, it's locked behind a password. Your choice is to do heavy troubleshooting and heavy tune-ups is really limited to those that have the password, which tend to be the manufacturer service people, and that tends to be expensive in some cases, or impossible to get if you're sending them overseas sometimes. So electronic engines have all these functions to them. Typically, we're talking to them now on a CAN bus that sends signal back and forth to the engine. And we have CAN bus mapping that goes on. We used to joke around and say the only thing standard is the name 1939, because the mapping can be different. That is, we can send, for example, to a CAT unit, you can't send a start signal down the communications link. You have to have a hardwired start-stop signal going to the ECU to get a CAT to run. A Volvo, they will not accept a digital contact start-stop. Everything must go through the communications link. So different manufacturers have kind of taken some individual approaches on how they implement their control system. You can't just say one box does all, because sometimes you have different engines involved. So you have to know what those are in order to implement these. So here's an ECU. You might have seen one here. This is I believe a Blue Star MTU ECU. Here's a CAT ECU on a gasser. Look at all these wires and connections on here. They got knock sensors. It's I think a 16 cylinder. So they had one of these for each bank of 8. All these temperature sensors, knock sensors, all these kind of things. Lots and lots of wires in this ECU. Here's an ECU on a diesel engine. Again, here's the connections on here. A very ruggedized case. Obviously, stand up to being mounted on the engine for vibration as well as heat. So very ruggedized processor locked behind some kind of password. Okay, so often you can have sensors that are on 1939 communication as well, and it protects the engine. The ECU is designed to primarily protect the engine, and it can be used for emissions control as well. So now let's look at when we're paralleling these islands, the systems together. You've got one gen, one load. you're going to have your voltage and hertz regulators. So we talked about, again, the control system we need for this unit. How do we pick the right controls? We have a stiff grid, and that is if we're pushing our generator up against the grid. In the US, most of it's a stiff grid, and that is your generator is not going to push the grid around. So that's a stiff grid. Where a soft grid is if you have two generators the same size and you parallel them, one can push the other around. So if you increase fuel to Gen 1, Gen 2 is either going to try to decrease fuel, or it may push back on it and go to inverse power if it's trying to regulate speed. So there's a soft grid and stiff grid, and that's an important discussion you've got to have when you're thinking of your control system. We had one in the islands. There was a small island in the Bahamas, where they had a series of smaller 300 kW, the biggest one, around the island. And they connected them together over the years. They never exceeded 12 megawatts on the entire island, the highest they ever had. But they wanted to go to a centralized generation system, and so they bought four meg units so they could have 12 and then a spare available. And they're going to do it all out of a centralized power plant. And when in the US, you bring these four generators online, parallel with each other. You close a tiebreaker to utility. You go to a KW regulated signal, and you would then just push the power on the grid to do your startup. Right, the grid can take 16 megawatts at any time. Well, on this grid, they couldn't. Right, as soon as they went online with these four gens, they stayed in a KW regulated, assuming a stiff grid, and they were on a soft grid. They actually became the grid. So when they told these engines to put out 12 kW, when the load at that island that day was only about 10, they went up to over frequency. So they went online, closed these new generators on the bus. They went up to about some frequency level, somewhere around 60, pushed all the other generators, 60, 61 hertz. They pushed all the other generators in the island off on reverse power. So bang, 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 all the small ones went off. They were the only grid. They kept driving themselves up even more because they're told to go to a certain KW level. It's going to push till it gets there. And it took a whole place down under frequency. So close the breaker, bang, 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 all up generators in the island went down. Boom, the big gens went down, over frequency, shut the whole place down. So the guy calls me up. He says, I can't talk long. I'm on a cell phone. Our tower's only got about an hour worth of battery, but our hopes the grid went down. So it took about a week to get all these little generators back up again. Nothing happens fast in the islands, and brought the system back up again because it was a stiff grid. It was actually on a soft grid. So make sure your control system is set up with the right information. And that is, if your generator can affect the voltage or frequency of the system, it depends if it's a soft grid or a stiff grid, right? If it's going to be a soft grid, you should have frequency limits incurred so that you can't push past that point. Or make sure you set the mode properly, not as a generator parallel with utility, but the mode would be generators in a parallel power island. You became the utility when they closed those breakers onto that grid on that island. So instead of being a KW regulated, this should have been a speed regulated system at that point. And you're seeing this more and more. We're seeing this with the micro turbines, with wind turbines, with solar, things like that. We're seeing microgrids all over the place now, much more so than we did 20 years ago, as people bring on alternative energy sources. So you'll see these before. People use these terms like auto, island, and standby prime. Keep in mind that these are actually least standby and prime are really an engine operating condition. People use them as a power system condition, but really it's not. It's really an island mode, if you will. And it can be one generator in an island, or it can be several generators in an island. And the thing I don't like about the term auto, and it's probably one of the most abused the terms out there, is you can actually be in auto and not ready to run. Okay. I feel that if for some reason you're not ready to run, you should force yourself not to be in auto anymore. But some systems actually can be left in auto and have a signal that's required by NFPA and the standards to signal if your system's in auto or not. So you leave your system in auto, but it still may not work. So it's you have to be careful of that term. Make sure you understand what the customer really wants as far as the definition of auto when you do it. An island can have multiple definitions, one load feeding one or several gens feeding one, standby and prime. So different terms. Make sure you know when you're talking to your people, your customers, what term they mean for what application. Okay. So in individual operational modes, you can have island or standby. You can have the gen is usually AVR controls the generator voltage, governor controls the speed, and you feed a load. Very simple, right down to a little pull start generator you buy at your hardware store. This is an island, right? This is an individual island mode. One generator, one load. You can do one generator to the grid, and this becomes a generator in grid support mode or a KW regulated system. So until you parallel as frequency regulated, then you parallel with the grid, you switch over to KW regulated, and you say, put out so many KW. And it'll fuel up, put out so many KW. The VAR is controlled by the power factor or the VAR controller, says increase excitation to maintain a certain level of VARs in the system. And you can accomplish such things as export, that is, you pump power out into the system. That's typically what is I need power in this corner of the grid, so we're going to turn this generator on, this distributed generation machine out in the middle at the end of the line, put him on line, push power out there, and I want you to put out, X number of kilowatts as determined by the dispatch center. The other one is peak and flopping that more in just a second. They require some local load for those to come, and so does import. So the next is if you have parallel generators feeding a load. So this is a parallel power island feeding. Now, this may not be one load. Okay, this may not be one load breaker. It may be 30 load breakers, but it's one load. There's no other source in the system. Although we consolidate it for this discussion all into one breaker at one point. Again, it might be 30, 40 breakers. We don't know, but it's one set of generators driving the load. In this case, we have to consider such things as FUD, good old Elmer. First up, discrimination. And that is when you send a start signal to, in this case, 5 generators, you send a start signal to 5 generators. Back in the day, they'd never start at the same time. The first one come on the bus, it says, I'm ready to go on. It looks at the bus and says, the bus is 0 voltage. I'm going on the bus, close my breaker. Well, the problem we run into is that some of these generators would come online and be almost ready at exactly the same time. They both look at the bus and see no voltage and close their breaker at the same time, out of phase with each other, and bang, one of them's going to lose and come down, maybe both of them. So now we've employed this FUD, this first up discrimination, also called multiple circuit lockout or dead bus arbitration, or different terms for the same thing. And that is the first generator up says, okay, I'm ready to go on the bus. Is anybody else ready? I want to take it. All the other gens respond, I'll wait for you to get on the bus. So it's a double handshake. I'm ready to go on. Are you there? I'm here. I'll wait. I'm here. I'll wait. I'm here. I'll wait. So they all wait for the first one to go on the bus, and then they all synchronize to the first one. So that's, in a nutshell, what first up discrimination is, what FUD is, multiple circuit lockouts is. Prevent multiple gens from going on the bus at exactly the same time. These multiple gens then feed a utility, and there it goes. There's the grid. And in this case, we should have a local load breaker here too. We didn't, sorry, I had a mistake on my animation. There's a load should be here. The last example is multiple gens with the load and the grid. In this case, you get your export, import, peak shave, things like that with the grid, and your local load should be here. I have an animation error here. So multiple gens feeding a load, multiple gens feeding the grid, multiple gens feeding both a load and a grid. All these require increasingly complex control systems. PPI, the parallel power island, there's certain functions that you should think about when specifying one of these. If you're going to go to a remote location with several different generators on board, your sources might be solar, wind, might be some additional IFG in addition to the parallel power island from your RICE equipment. So you have to consider fuel optimization, generator management, load management, runtime management or equalization, ZPT, heavy consumer control, and run-up excitation. So we're going to cover these in a little more detail, but some of them are pretty easy. Runtime management, it used to be runtime equalization. We tried to run our generators in our parallel power island with about the same number of hours in order to keep them all wear and tear equal on the machines. Well, the problem we run into is a year down the road, they're all ready for maintenance at the same time. And I have to shut them all down to maintain them. We got to shut our bus down. So, well, let's rethink this a little bit. So we're going to intentionally run some machines more than others so that when it comes time to do maintenance, we can take generator 1 offline and maintain him and run off 2, 3, 4, and 5. And then we put 1 back on and maintain 2 and run off 1, 3, 4, and 5. You get the idea. So it's managing the runtime hours so that we're not already at the same time. Okay. And then ZPT, zero power transfer, is minimizing system disturbance or wear and tear on switchgear and equipment by driving the generators down to a very low power point and then opening the breaker. So that's one definition, is when it comes time to take a generator offline, you reduce his fuel until watts get down to some low level and then open the breaker. So zero power transfer. At zero power, we transfer, we open the load. Or as you're coming on, you'll bring a generator on the bus, flows it in sync, so very little current flows until you start to increase the fuel. Then current takes over and you back off the other one. So transferring power from one to the other at a low kW level to save wear and tear on the system. The other definition of ZPT, and this is one utilities don't like as much, but we see it a lot in the northeast part of the US, is that you run your generator plant. You have a local power plant with a local load and a utility tie, and you run your local generation to equal your load being consumed on your system. So there's zero power at the utility tie point. Sometimes it's called storm mode. So you have a storm coming, you want to kind of support your load. You got both your generator and your utility system available. If one fails, the other's right there. Utilities don't like it because they're not making any money. They're not selling any watts, and so they're not making any money off ZPT. But it is a common storm mode, or data centers call it storm mode. Let's talk about some of the others in a little bit more detail. Gen Shed Gen Ed is also known as generator management, and some call it load demand. I put that in smaller font on purpose because that's not a good term to me, but that's some use that term. It's the idea of adding and removing generators from a power generation system in order to get your right amount of spinning reserve and optimize your fuel efficiency. So it's adding and subtracting generators as needed to maintain a certain spinning reserve. It don't necessarily have to be the same size anymore. At one time, we always said, make sure your gens are the same generator, same parallel, because that's when they're analog load share. Now that the digital stuff is not necessary, you can run different size units in parallel with each other just fine. Watch your winding pitch, of course, we talked about that yesterday, but the actual size doesn't matter that much. And you add and subtract generators to maintain a condition, if you will, a spinning reserve condition. Typically with a 5-gen system, let's say you have an outage, you start all 5, or you send a start signal to all 5. Hopefully they all start. If they don't, you're still okay. You only need 3 to run. You send a signal to all 5. Once you get 3 on the bus, maybe even all 5 on the bus, you maybe wait half an hour to get them nice and warm. Then you start taking off the unnecessary generators to save fuel and just run on the 3 you need, keeping the other 2 in standby, if you will, cold standby or operating reserve. So that's Gen Shed Gen Ed. Load Shed Load Add is a way to protect a system. So let's say that you have 5 gens and 5 loads. So you bring all 5 gens on, all 5 loads are up, everybody's happy. Now you don't need, because your load is low, you don't need to have all 5 gens. So you back off 2 of them. So you're gonna have 3 gens feeding all 5 loads. Well, let's say you lose a gen. and it might just go into alarm and come off slowly, or it might be a trip stop fault condition. In that case, you're loading the generators. So you'll take off your lowest priority loads in order to maintain your highest priority loads. The analogy is the operating room at a hospital has highest priority. It's going to stay on. And some people say it's the boss's coffee pot, but whatever. You maintain your highest priority loads by shedding the lower priority loads. And so once you get more generation back on, so our scenario is you're running 3, you trip 1, now you got 2 and you need 3. So you start the other 2, get 1 good one, and now you can bring back on all your other load. So load shed and load add often work in conjunction with gen shed, gen add. I will, Wayne, in just a second. The gen shed, gen add, load shed, load add come into play to protect and maintain the highest priority loads and still maintain a solid operating system. So it's often combined with generator management. Let's take half a step back to Wayne's question. Can you explain ZPT with reference to storm situations? Okay, zero power transfer is the idea of running your generators to equal your local load. The scenario is utility feeds the bus, gens feed the bus, loads off the bus. So normal conditions in a bright sunny day, you have your generator shut off, drawing power from the utility. Storm comes along, you fire your generators up, you increase the fuel on your generators to equal the load being consumed by your local load. So the power you're buying from the utility is minimal or zero. The term is zero, but it might be zero, it might be very low level. We used to have we actually had tied into the weather system that would automatically start generators and move them into ZPT mode, what they called storm mode, when the storm was coming. And once the storm and lightning was over, they would then shut the generators back off again and let the utility take it. So very good. Heavy consumer control. In this case, you're trying to reduce the lowest possible spend. And so let's take, for example, a drilling motor at a oil and gas exploration site. You got a small generator that feeds the air conditioner and the control trailer, right? Gives them control power, living quarters, that kind of thing. Maybe a 20 or 50 kW generator does all the auxiliary equipment. When it's time to run that big drill motor, it won't run off that little generator. So you start up the big motor, the big generator, and you run your drill off that. So heavy consumer control is increasing the spinning reserve. Remember what spinning reserve is. You're increasing spinning reserve to a level that will accommodate the oncoming load. The other example we use is a container crane on a ship. The guy crawls up into the container cab and he pushes a request to start button. That request to start is actually increasing the spinning reserve set point to a point that all the generators start. Once they all start and all on the bus, then he's given a permission to start coming back. He says, okay, you may now start moving the crane. So then he does his crane stuff, pulls, unloads or whatever. Once that's over, we don't need that spinning reserve anymore. He shuts the cab door or closes the system down, and our spinning reserve drops back down to a low level again, and it sheds the generators that we don't need anymore to optimize our fuel. So that's heavy consumer or load control. Okay, here's an example of one we did in South America. Noriega shut the gas down to his neighbors doing all that stuff going on in Nicaragua, and they had to have power, so they brought in 200 megawatts of diesel, one container at a time, and dropped them on the ground, connected them all up, and fed their local utility off of diesel. This is just being built still. The tanks aren't on site yet, but you can imagine there's some big fuel tanks goes along with this as well. And I asked, do you want to pay the fuel bill? Well, in this case, we want to optimize our fuel consumption. Now, nowadays we'd probably put solar on site because that's a nice sunny location and probably at high altitude. You probably put solar on there too. Back then we didn't have it; the option wasn't there. But so we talk carefully about fuel efficiency, and we have that in the form of generator management. So we use GenShed GenAdd to run a certain minimum number of generators to achieve this level of fuel efficiency. We don't necessarily have to have the same size gens, but we also run fuel optimization, and I'll give it to you. But a generator engine generator combination is most efficient, not at its nameplate 100% value, but somewhere around 75 to 80% of the full nameplate value is where the engine is most efficient. Now, of course, we're not saying total power, we're saying efficiency, power, fuel in, power out calculation, right? And so some gens can actually run at different values. So you have a certain anchor gens that hold it. Let me talk a little bit more about this. Let's take a look at some numbers real quick first. Here's actual curve. I got this from a Cat C17516 because it's available online. I'm not picking on Caterpillar. I just happened to find it online, so I used it. This actually is the efficiency data for this machine. It's showing somewhere just shy of 40% efficiency, maybe 37, 38% efficiency at 75% of the nameplate, the engine nameplate. See, it actually decreases to lower efficiency at 100 and lower efficiency on this side. So you want to optimize that and run at this point. Here's the generator efficiency curve for a Stanford 1760 kVA. Actually, you can see it here too. Here's a power factor of 1, which you don't often run there, but at a power factor of 1, your efficiency peaks out somewhere around this 75 to 80%. It's a much flatter curve, but still it peaks out in that same range, right? So let's put them together. Excuse me. As you know, when you're looking at efficiency, you multiply them together. So it's 0.37 at the engine efficiency times 0.96 of generator efficiency gives a net efficiency of 36%. So this net efficiency value is plotted on this chart to the left over here, and we see a definite peak at right around 75%. So 75% of nameplate KW is where this machine's most efficient. Let's take this one step further, and these are obviously made up numbers, well, based on true numbers, okay? Again, we're picking on the 175/16. At 3,000 or 3,000 kW, it burns 213 an hour. At 2250, it burns 154 an hour. If we assume a 9,000 kW load, okay, this is where I'm taking a little liberty with the calculations, but it just makes it so pretty when you look at it. But if we assume a 9,000 kW load, you can achieve that with 3 generators, all running at 3 times 3, 9,000 watts in it, 9,000 kilowatts in this case. On this machine, you can also achieve that by running 4 gens at 2250. What's the difference? Well, first of all, you run 3 gens equally sharing load, your gallons per hour is 639. You run 4 gens with fuel optimization enabled, you're running a total of 616 gallons an hour. Okay, not a big difference. But when fuel costs you a lot, and you're talking, this is just 4 machines, you're talking 200 kW of power instead of 900 or yes, what was I say? Yeah, 2 megawatts of power versus 9,000. Anyway, the 4 gens run at 616. What really makes a difference here, what really helps you out, is that if you want to add more load to your system, in this 3-gen system, you have no spinning reserve left, right? Spinning reserve each configuration is 0 down here. With this is 3,000 on this one. So you can add more load to a system without having to start machines. So you're going to increase your running hours, but it's not at full power. So that helps you wear and tear a little bit. You're going to have to start and stop more machines at this point. So there are definite advantages to fuel optimization. Again, these are made up numbers, but you can see that the obvious difference here is that think carefully about your fuel consumption. We talk about nowadays adding gaseous fuels injected into a biofuel type machine. We'll look at more efficiencies due to inverter fed generation inputs from solar or wind or hydro or whatever's available. So I'm sure fuel consideration is important to a lot of your applications. We used to do a lot with the military, and I heard some cost of fuel delivered to the front lines for small gen sets was $400 a liter or some darn thing. Time they got it there, and that's not counting human lives. So it can be quite expensive. Okay, we're doing okay. So let's talk about peak lopping, peak shaving, and IRC. In this case, these are different terms that we use to share the load between the utility and the local generation. Again, your concept is generator feeding the load, a load bus tied to utility. So utility, load, generator. Your load profile, and this is, you should have this whenever you're doing a system development, will say, I expect my load profile to be throughout the day. This is time across the bottom axis. It got cut off a little bit, but this is midnight to midnight. So peaking out in the middle of the day. And again, these are made up numbers, but it illustrates the point. So as your load comes up during the day, at some point, if you're peak shaving, you start your generator. So the red is the generator power. The green is what's being purchased from the utility, and the blue is your actual load profile, how much power you actually need for your load. If you go to your utility and say, I promise I'll never buy more than 50, just made up number game here, I'll never buy more than 50 kW from you. Okay, we'll put a smaller line in and your monthly charge will be less. So you say, okay, I'll agree to that. And the way I get around that is I'll start my generators up when we get close to 50. They'll take on the load, pardon me, they'll take on the load as we go up, and you'll see the generator in peak shave power goes up when this goes up. At this point, we came back down a little bit, but we didn't actually reduce the output of the generator. We let the utility drop down a little bit because we never want to go above 50. And so throughout the day, then the generator ended up taking over the numbers. As we started to come off in the afternoon, again, the load came down to some point where we could safely shut off. We're not stopping right at 50. We have hysteresis in here to keep from stopping, starting. So we actually come at some other point. In this case, in my example, I said 40. We shut the generator off and let the utility take on the load. So that's peak shaving. You have to know the power at the utility point in an analog value, or it could be digital, but it has to be a variable value of the watts at the utility tie point in order to make this work. But it's a good way to go, used very often, especially in areas of constraint or areas of where you have high incident costs. Good example of this. I live in Arizona. They're building houses like crazy out in this part of the country, and the lines just didn't become overloaded. So if you put an industrial plant out here somewhere, they couldn't get a lot of power out of it until they put in new lines. So that's very expensive. So they'll charge them a high rate above a certain kW, encouraging them to go to peak shaving. Peak lopping was developed by some other controller friends of ours, and their term is somewhat similar. They're looking at, they only need to know, instead of the actual value of watts being purchased from the utility, they only need to know that the load has reached a certain level of watts. So when the load reaches a certain level of watts, in this case 50, we send a start signal to the generator to run in parallel with the utility. And as long as the load's above 50, we run the generator in parallel. When the load drops below 50, we turn the generator back off again. So we don't have to know the actual value of watts. We just have to know that our load, which is local to the generator in many cases, if the utility tie point's a long ways away, we don't have a way to measure that power. We will just take the local load and say, at some value of load, we run our generators. And that's peak lopping. Take the top off. The difference is, of course, your generator runs up to its nameplate value, if you will, and stays there all day and then turns off. So it may not be the most fuel efficient way to do it, but it's one step easier on the control scheme. IRC is called interruptible rate contract. An example of this would be a standby rate or ATS and load. You go to the utility and say, what's your IRCs or what you offer for that? And they'll say, okay, if you agree to let us take you offline when we get in times of constraint, if our grid gets stressed, we'll take you offline for a max of 4 hours, for a max of 10 times a year or something. And at that point, they'll send you a signal, says, okay, get offline. You start your gens, you take over your load. So you can't see the colors here very well, but at some point we got a signal from the utility, get off my grid, and you started your generators. They took over, the gens ran the whole load, utility went to zero. And then at some time later in the day, it said, okay, now you can come back on again. And we synchronize back to utility and shut the generator off. So that's example of that would be an ATS transfer switch in online test mode, that you can accomplish that very simply and get this IRC discount from the utility. It can be significant. I know some people that have got it around here, and some at my brother's in Illinois, and he's got it. So there is some economic incentive to do these things. Okay, 45. Okay. Run-up synchronization is a method that we used for a while and then kind of fell out of favor in the 80s because of electronics. And now that's being used more now. But it's really a quick way to bring multiple gens on. And we have to go this, we're running out of time. Let's speed this up a little bit. But it's called closed for excitation, dead bus paralleling, dead field, run-up sync, are all the same term for the same thing. Just different people use the different terms. We did it at University of Miami hospitals. We got 3 2.5 meg Kohlers up and online repeatedly in 6.7 seconds. That's pretty amazing. 3 big machines online in 6.7 seconds. The big advantage here to them was that they actually could start less. EPRI data, 98% of the averages in the US last less than 2 seconds. If you have a classical system, you can't wait that 2 seconds. As soon as you have an outage, you're standing to start through those gens and you're cranking, you're going, because you've got to get there within 10 seconds to meet NFPA 110, right? So you've got to move fast. System, you can wait that 2 seconds, knowing that you'll be able to get all 3 of them online in 6.78 seconds repeatedly. And so it's a huge savings on starts and cranks. And it's also used at this same power PPI in South America. These 480 volt machines, a bank of them, all fed transformers. And then at that medium voltage point, they were put into the substation on the right. Well, you couldn't, it's a big transformer at 40 volt level, and you couldn't energize it off one machine very well. So you soft start that transformer. You start one gen, use CBE to soft start the transformer, magnetize the transformer, if you will. Then you parallel your other machines to it. We're able to achieve a 27-to-1 ratio. So that is one generator can pick up 27 times its kVA in transformer, which was a huge savings to them not to have to put a transformer at each generator. Mexico, starting large motors, you got a 1-to-1 ratio. They're actually able to start a 100 kW motor on a 100 kW generator. End of a long line, soft line, couldn't get there, and it worked. So quickly, what it is, you start with your some protections disabled, 27 under voltage, 81 over frequency, 24 volts per hertz. You disable those protections. Your load breakers are open, your generator breakers are open, and you're ready to, exciters are disabled. So you're ready to start in this condition. If you need to start at that point, you send a start signal out to load breakers stay open. You send a start signal to all the generators. You tell them to go to idle, and our simulator's not working. I have the numbers that simulate it's not working here. But anyway, you send the gens to idle. The first 2 make it okay. There it goes. The first 2 crank up to and start and fire up. Once they get to 1,000, which in this case is idle speed, they close onto the load bus. Onto the generator bus, not the load bus, the generator bus. The third unit in my example didn't start. So this is a 2 out of 3 scenario. You got to have 2 to feed the load. You got 3. The third one didn't crank for some reason, just didn't fire. You can hold her for a little. If you don't, you can go ahead and continue. If you continue, then you lock out that third unit and say, you can't go till I get done. But I only need 2, so I'm going. So now I got my 2 gens and I'm good to go. I'm going to go ahead and turn on the exciters, let the speed ramp up at somewhere at excuse me, at about 1260 at this 1000 or so, just above idle. We'll act 70% RPM. The exciters are enabled. The ramp is started, and I say this carefully, from 0 amps DC, from no excitation current, to 100% AC volts. And I say that very carefully. It doesn't take much excitation current, maybe 10%, to achieve rated voltage with no load. Remember we talked about that yesterday? So without having to have this, you can actually start up and bring it up to 100% voltage. And so it's ramping up. Your machines are accelerating. The fuel is being added. The alternators are accelerating together. The breakers are closed. The excitation is coming on, and it pulls them into sync. It pulls them into sync and continues to ramp up towards rated speed. When you hit your value of voltage, which is, the gensets will put themselves into sync. The load breaker is still open now. Your AVRs are on, your generators are on, you're putting out voltage. You're not quite the full voltage yet, but you're coming up, your frequency is coming up, and the other units are locked out. You can't run. We're going to run these two. When you get to about 95% volts, so 456 is 90% of 480, 57 hertz, 90% of frequency, you say we're good to go. Turn on your protection. Your 27 under voltage is turned on. Your 81 under frequency is turned on. Your 24 volts, those are all turned back on again, and your load breaker is closed. So protection on, generators on, breakers on, loads being fed. Now you can have this last one that had trouble cranking. He can go ahead and crank. You come on up to speed and synchronize with a normal synchronization process and feed the load when he's available. But you don't need it. You got two. You're good to go. So that was a pretty quick list. Okay. Looking at the question real quick. Think about this closed for excitation process. Can you provide guidance to what these? Tyler, good question. Could you provide guidance on determining whether to use a medium voltage generator or a 40-volt generator with a step-up transformer for a medium voltage system? Yeah, it's availability. Medium voltage generators, I would say probably around 1.5 megs to 2 megs would be where I'd start to look at a medium voltage generator. Medium voltage generators are obviously more expensive. The overall system cost might be less if you didn't have your transformer, but you're tied into that generator. They're not as common and not as available, where if you had a 480 volt with the step up, you can find those pretty quick and pretty easy if you have to. So it's more of a maintainability and service part. Efficiency doesn't really matter that much. It's really more a matter of components and system cost. If you have 3 or 4 generators, each being in the 1.5 to 2 meg range, and you need to add transformers for each of them to get them up to medium voltage, that can be a lot of money, where you get cheaper to go with the medium voltage. The other consideration is conduit, conductors. Medium voltage, your conductors is significantly smaller. The cable costs more per foot because it's got the shield on the outside of it, but the copper cost can be significantly more on low voltage. So rule of thumb, I'd say 1.5 to 2 megs in that range. I haven't seen many medium voltage systems below 1 meg, and that's pretty rare. Okay, so now we're on the bus and feeding the bus. That kind of sums up the closed for excitation. Now I want to talk just a minute about protection and hook. I'm going to play a quick video for you of a golf course in Florida when started an arcing fault. It's kind of interesting to watch this arcing fault. Sorry, technical difficulties here. Protection didn't clear it. Value system, and then it farts off a big cloud of acetylene gas and ignites and burns up. And see all the oil burning. So you don't want this. all available units. As my friend Terry says, if he was watching this, it'd be getting smaller and smaller and smaller. I'd go the other way. I'd go towards it. But anyhow, I love to see electrical things go haywire. I spent so long fixing them myself. But this is what you don't want. So we're going to talk about protection here for just a second and wrap up the day on protection systems. And this is what you're trying to prevent, the arcing. Real quick, I do want to talk about the right rotation and the wrong phasing, why that's important. Here's our scenario. Imagine you put in 2 new generators. When you pulled the cables, they rolled the phases at one of the generators, okay? So that's just what happens down here. When they check the rotation here at the switchgear, they're checking rotation of one to the other. They say, oh, that's wrong. I'm going to roll 2 phases, right? So they roll 2 different phases. So is BCA the same as BC? Think about that for a minute. Medium voltage, harder to maintain. We'll get back to that, Matt. Just hang on a second. Now you now have the right rotation because ABC is the same as BCA. BCA, 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 ABC, same thing, right? So we have the right phasing here. What do you think? Does it matter? Will this work? What do you think? Your phasing is correct, and it will work. If you're paralleling 2 machines, this will work. Where it'll bite you in the fanny is that, let's say you're working on a system one day and you're looking at different currents and different phases. The A phase current here on this machine is not the same as the A phase current over here, because A phase rolled over here to C. So now you got to look at A phase. Say you want to balance currents in the machines, you got to balance between A and C. Sometimes your VAR power factor regulators can give you a problem if we're only looking at a single phase, because now you're looking at the relationship between A and C over here and B and C. So while this will work, and it's done probably quite a bit with different machines, when it comes to balancing and reading, it can cause you problems. So be careful of that. Now let's take it one step further. Now we've got 1 gen feeding the double-ended substation. Okay, we routed the wires through different paths to provide our isolation, maybe even 2 breakers off the same gen, provide isolated separate paths in order to accrue some type of backup redundancy. So 1 gen feeding the double-ended sub. Is the sequence correct here? So it's A and B and C. So yes, those are as correct. Is the sequence here this correct? Well, it's BCA, so the sequence is correct. Of course, what will happen if you close the breaker here? Yeah, it's what we call a fuse tester. You only get 1 test and it's done. But it's obviously going to bark that breaker and kick it back open pretty good. So I should say the best way to check rotation here is 3 voltmeters across these guys at the same point. They'll go up and down together. They'll sync different ways together. So you'll watch that how they're all the same. But you need to check the phasing in addition to the phase rotation. Okay, keep that in mind doing startups. So we're going to talk about faults in a system. Current faults, short circuit faults, overloads and impedance faults, and power faults. I am probably going to run over by a few minutes, but I'll try to wrap it up by 10 after or 5 after if I can. We're trying to protect in the generator the systems we talked about the other day, the insulation system, phase to phase, phase to ground, turn to turn, the conductor system against overcurrent, overloads, and the interns across here, and the exciter components that are out there too. So we're trying to protect these systems in our generator. Of course, vibration as well, but that's a third-party aftermarket. We don't do that directly. And of course, shaft current. You want to protect against that as well too, and that prevents pitting on the journal bearings. We'll talk about that more later if you want to. It's put together in this assembly. We talked about the line to turn short, the phase to phase short, and the phase to ground fault are the ones we want to detect and protect against. In generators, we don't normally use fuses because of negative sequence currents, and that'll burn the interns. So it's bad for a generator. So we equip breakers with a thermal mag or an electronic trip and trip coils and auxiliary contacts and all these things to put into the breaker to make this system protect as good as possible. Electronic trips nowadays have lots of options on them. It allows you to do different things with them. Voltage taps, so you can even get reverse power, under voltage, under frequency, can all be part of the circuit breaker protection now if you want to put it at that level. We often also use relays, and this will talk some more about medium voltage here, is why do we use relays in different schemes and we different types of protection. For example, if we have a fault here, right, will this breaker detect this fault? Obviously not, right? The second location, it will, right? So you have a fault between the generator and the breaker, it won't be detected. Here it will be. So we won't trip, we'll sit and burn the generator up. But if we use a CT, the CT can detect the faults here, or here, or here, or even here. Any of these locations, a CT here on the neutral leg will find that, or a set of CTs in the phase will find that. So also in medium voltage machines, we'll use CTs on this side because the voltage here is 0 to ground. So we can use a low voltage CT in a medium voltage generator. First time I saw that, I about freaked out. But they do it all the time because it's so much cheaper to use a low voltage CT, and it's a lower current level. Now let's talk about grounding for a minute. Probably not the best way to ground, but in this case, I can see some poor painter hauling a bucket of dirt up several flights of stairs to ground it. At least he could have used a metal bucket. Anyway, grounding is important in your system. So the fault current depends on how you're going to ground. You're going to go solidly grounded, resistance grounded, and how you're going to detect and protect your system. There's reactance grounded and ungrounded. So solidly grounded, resistance, reactance, and ungrounded are the different types of grounding systems out there. Ungrounded generator, quite common in marine applications, prevents cathodic erosion, etc. But there's a way to detect a ground even in an ungrounded system when it inadvertently has grounded one point in the system. When you're doing a coordination study or you want to protect against the generator thermal limit from being burned up over time, this is the breaker settings to protect that unit. Here's a real-time current curve showing this. In this case, we had this is for VA hospital out of El Paso, Texas. We had this. And so here's the breaker curve. And in this case, we have a fire pump. We want to make sure it's protected against having a problem or a cross of the curve. And so here's the long time part of the curve, the short time, and the instantaneous part of the curve of an LSI unit. So coordinate these. We have a generator limit and then a generator breaker and a feeder breaker. You're putting a system together with a generator, main breaker, feeder breaker after it. You want them coordinated so they don't cross. So here's a time current curve showing the largest motor, again, is plotted on here. And we have a feeder breaker, 800, 1200, 500, and the 1200 amp main. So here's your 800, 400, 400, 1200, and 125. And they're all plotted on the same chart looking for where they cross over. In this case, we have a coordination issue where the red and the blue are crossing over each other. Okay? We plot these curves out, determine these settings. We want to watch out for this crossing. It becomes an uncoordinated system. And that analogy would be you have a fault down a feeder breaker, but instead of tripping that feeder breaker, you trip out the generator main breaker. You don't want that, obviously. To do these studies, we have a power system study. I wish I had more time to spend on this, but be careful with your power system study. It often gets forgotten. It's dependent upon every parameter you can think of: cable type, cable length, conduit type, connection type, impedance of the transformers, impedance of the generator. All this goes into figuring this power system study. Types of load, VFD, LED, have high harmonic content, all these things. And so everybody says, I can't do it. I don't have enough information. That often gets overlooked. So make sure you have this in the back of your mind. Somebody needs to be doing this short circuits, this power system study, of which part of it is the short circuit study. to determine all these different factors, cable size, duct type, it's a plastic conduit versus an EMT or rigid, all make a difference on that. And you want to end up with good coordination where you don't cross each other and yet you provide as much protection as possible. And here is another time current curve of a well-coordinated system, very tight, but good coordination between a 1200 amp breaker and 800 amp breaker. It's like there's two 1200s and an 800 amp breaker. Okay, well coordinated. If you give a fault, now the currents along this axis on the left side, I'm sorry, top left axis, currents along the bottom axis. As you go up in current, at this current flow, you'll never trip. At this current flow, you'll trip right here. Okay, so that's what that is, time current curves. When will you trip at what value of current? Ground fault is checked as well. And a summary table is created with all these values in here. And so we're looking at each device in the system and the ratings. In this case, it's AIC, amps interrupting current, or WCR, and withstand current rating. Remember, we talked about the asymmetrical part of the curve. The X double prime D calculation was the peak value of current, and the X prime was where the breaker has to clear. And so that's the AIC rating. And so the AIC rating, that device is there, and they calculated what the current would be at that point, and that tells us that we're well within the rating here. So we're okay on all these units, right? Here's an example of one that's uncoordinated. So R, G, B are the three main and two feeders. Here's cable melt out here, this red line, and B and R are not coordinated, or B and R are okay. Blue and the red are okay. The green and the red are not coordinated right in here. And so it's highlighted, said, hey, we got to change these settings. Otherwise, if we have a problem down here on the green feeder circuit somewhere, you'll trip the main breaker before you trip the feeder breaker. You don't want that, obviously. Arcing faults, like we saw up front, you want to prevent that. In that case, we use a voltage controlled or voltage restrained. That is, as the impedance increases real high, the voltage tends to drop. As the voltage drops, you want to trip faster. So this is detecting both current and voltage, and at a high level of current, often with a suppressed output voltage due to this fault, pulling the voltage down, actually trip at a lower value. Prevent those kind of arcing faults we saw at first there. And we have differential relaying, and it looks at power in and power out. Reverse power, which is not differential, but it's a power flowing back into the engine, and it's driving the motor, the crankshaft. And then reactive power is consuming bars off a system. Just when you thought you understood lead lag, make sure you talk to your customers, right? That some of them think that leads on the left and lags on the right. Well, you increase your excitation, what's going to happen? Often in the utility industry, they say we're producing leading bars to supply the lagging bars of the system. So most of the industrial folks say we're supplying lagging bars to offset the lagging bars. So just get it back to the basics. If you increase excitation, you get more bars. And I stop there. I don't try to get the leading lagging discussion, because it can get hairy if you get somebody who doesn't understand this like you do now. So when you're parallel, your voltage and frequency sit there. I'm going to skip ahead a little bit. Differential relaying, it's a zone of protection. If you have current, it balances the current this side and that side. If they're equal, it doesn't trip. If you get a fault outside, it won't trip. So a fault out here, not trip, because the current here equals the current there. If you have a fault here, it will trip because this current does not equal that current. All right. So that's what a differential relay does. Very sensitive, very quick, very good protection. A little bit more expensive, but very, very good. It's very effective, very secure, and it clears faults very, very quickly. So quick summary. And Matt, to answer your question, are medium voltage and harder to maintain? Not harder. They're because of the voltage stress in there, you need to make sure they're kept clean, because a little bit of buildup of corrosion or or a little buildup of dirt in the system can actually cause a fault in the machine. So they're not harder to maintain. They're usually built with different specifications. It may be journal bearings instead of anti-friction bearings. They may be built. One consideration is partially insulated versus fully insulated. I don't have time to go into it now. I'll drop you a note. You can give me a ring and I'll explain it to you. But when you're specifying medium voltage machines, if it's a solidly grounded machine, you can get by with a lower cost, partially insulated machine. That is, the windings closer to neutral don't have as thick of insulation. If it's going to be used in an impedance rated system or a delta ungrounded system, then you have to go to a fully insulated machine on medium voltage. And that's the only time you see that's on medium voltage. And that means that throughout the windings, they're all insulated fully to ground. So it's not harder, it's just it's more strict, I guess you'd call it, on its maintenance. So let's talk real quick about a single island configuration. And this is the protection that's kind of recommended to help get you started. If you don't have settings, you didn't do your power system setting, you got to test your generator out. If you set it here, you'll be okay. Don't leave it there, put it back. But this will get you by in a little bit, in a pinch to get you by. Single generator, because voltage by the AVR, speed by the governor, load connection close to genset, low voltage, low power, no wind. So typically, if you do 50-51 at 110% of rated, you'll be okay. So this is your overcurrent protection to 110%. Over voltage protection, again, 110%, you'll be okay. 81.0, that's over frequency protection. Again, 105%, you'll be okay on that. You probably have a engine over speed setting that might be at the same level or maybe a little bit lower. So be careful of your engine over speed setting. The 46-47 negative sequence voltage and current, if it's possible to lose a phase, like you've got fuses in a system, set at about 20%, you'll be okay. Now, the generator doesn't care if it runs under speed or under voltage, but your load might. So if you have transformers and motors, you may want to protect them. In that case, you'd want to set under voltage, under frequency. This is not to protect the generator. This is to protect the load, right? And so if you're just load banking, don't worry about it. Load resistors don't care. But if you're feeding the load transformers and motors, then yeah, you probably want to set under voltage and under frequency. If you have a PPI, do the same settings plus reverse power 10%, reverse fars at 10%, differential if you got it at 5% with the 5% pickup and slope. Load, if you've got arcing faults, not farts, arcing faults possible, you'll want to use a voltage restrained or voltage controlled relay, perhaps. In that case, you could set them for 70% voltage and 100% current. So if the voltage drops to 70, they'll trip immediately. 32F forward power, often used in control schemes more than protection schemes, but 110% is reasonable. Put out more than 110%, you should trip off within a second or two. At the PCC, the point of common coupling, the utility tie point, you want to do such things as 32F, 32R, that's power out and power in at that point. You may want to think about those. Directional overcurrent may be required by the utility. 50 breaker failure, that is if you send a trip out and it doesn't make it, then you need to trip the next breaker up line. So that's a 50 BF. 51G is often required by the NEC, ground fault protection. Rock off, rate of change of frequency. So if you're running at some point and you have the possibility to island, that is your generator is feeding local loads outside your system within the utility scheme, then you want to rock off. Rate of change of frequency, you're going to go up over time or down. The chances of it be balanced perfectly are very slim. And so if you start to do this, you want to trip offline. UK had trouble with that, so they had to change that setting, but rock off been used some. Vector jump is very, very fast, very quick, very good protection, but almost too much. It measures the time between each zero crossing and says, if that time changes too much, I'm going to trip. Something happened to my grid. And so it's not used often because it is so sensitive. And then the 27, 59, 81, you are set tighter. So under voltage, over voltage, under over freak are set a little tighter. I made it 2:09. I got my hour in. Please fire off your questions. Thank you for hanging in there with me for a few more minutes. And if you have anything, bring it up in the chat box. I'll hang on for a minute.
Thank you very much, Steve. While we wait for those questions, everyone, the day 4 link should be coming from your leadership if you don't have it already. So keep an eye out for that. I understand you need the PowerPoints and the Zoom links, or excuse me, and the videos. Those are processing right now. I have my website up and the videos are in process. So you're going to get them all at once. I apologize for the delay, but you should be seeing those shortly. Thank you everyone for joining us today. If you have any other questions, please let me know. Remember, you can email myself or you can email Steve directly or any of the other instructors throughout the class. Thank you again, and we hope to see you tomorrow.
Be safe out there, everybody. Thank you for your time and attention.